Hello everyone, and welcome back to Mitchell's Physics Review. Today we're doing rotational energy. Let's take a look at our problem. A 13.5 kilogram object and an 11.5 kilogram object are suspended, joined by a cord that passes over a pulley with a radius of 10 centimeters and a mass of 3 kilograms. The cord has a negligible mass and does not slip on the pulley. The pulley rotates on its axis without friction. The objects start from rest 3 meters apart. Treating the pulley as a uniform disk, determine the speeds of the two objects as they pass each other. So first, let's look at our givens. So, the radius of the pulley is 10 centimeters. The mass of the pulley is 3 kilograms. Mass 1, which is on the left side, is 13.5 kilograms. Mass 2, which is on the right side, is 11.5 kilograms. And the height in between them is 3 meters. We also know, since this is a uniform disk, it has a moment of inertia of 1/2 mass times radius squared. Next, we can draw an LOL, or an energy diagram. First, what's in our system? Well, we need both of the masses, the pulleys, and the earth, because the masses are suspended in air other than the 0 point. So the earth will be the gravitational or potential energy, and the masses and the pulleys are what's going to be used for kinetic energy. So we start all at rest, and we start with only gravitational energy because the system is not moving. But at our final position, when they're meeting up, they are moving downwards because they're accelerating downwards, as you can see here, because this one's heavier, pulling this one upwards. So now we have a potential energy and kinetic energy in our final. So this problem can be quite difficult if you try and take it all in at once. So why don't we start by breaking it up in individual pieces? First, we know that the initial energy is equal to the final energy because of the law of conservation of energy. So we can also say that the final energy is equal to the potential energy of mass 1, the kinetic energy of mass 1, the potential energy of mass 2, the kinetic energy mass 2, and what most people tend to forget, and what I struggle with remembering, is the rotational energy. That is a big part that we need to add on, otherwise we will not be getting the right answer. Personally, when I first did the problem, I forgot about it, and it led me to a wrong path, and it's a bush you don't want to go into. So, after that, we already said that initial energy is equal to final energy. So we know that our initial energy is equal to UG, or potential energy of mass 1. Because if we call this our 0 point, we know that the only energy is right here in mass 1. So we know that potential energy is equal to the equation mgh. For that, we're going to plug in mass 1, which is 13.5, g, which is 9.8, and h, which is 3 meters. So the height, gravitational field strength, and the mass. Then we can just plug that into our calculator and get that the initial energy is equal to 396.9 joules. Since initial and final are equal, we know final energy is equal to 396.9 joules as well. Now we can go on to the rotational energy. We can call rotational energy Kr, or K3, however you want to set up your equation, if you want it to be called the third kinetic energy or the rotational kinetic energy. So we have Kr is equal to 1/2 moment of inertia times angular speed squared. We don't have the angular speed, and we're looking for velocity. So let's try and put this in terms of the velocity. So we can do that by plugging in our moment of inertia for a uniform disk, and then using v over r squared and substitution for omega. So what this is going to do, it's going to allow us to do algebra and simplify the equation to 1/4 mv squared. we're going to plug in the mass of the pulley, and then we get 0.75 kilograms v squared. Now, usually when we solve an equation, we don't have two variables. We don't have kr and we don't have v squared. But why do we have that in this one? Well, since we're going to be doing multiple little parts to get the whole, we're going to need v squared later on in the equations because that's what we're solving for. So in this case, it's okay that we have the rotational energy is equal to 0.75 kilograms times velocity squared. Next, we can look at the two different potential energies. So potential energy 1 is equal to mgh, or mass 1 times g times the height, which is 13.5, 9.8, but this time the height is 1.5 because it's when they meet in the middle. So the middle of the height is just going to be 3 divided by 2, so 1.5 meters. You plug that into a calculator and get the potential energy 1 is equal to 198.45 joules. For potential energy 2, we have set it equal to mgh. We use mass 2, which is 11.5, times g, which is 9.8, once again times 1.5. Plug it into our calculator and get 169.05 joules. Now we can finally solve for our two kinetic energies. For kinetic energy 1, we're going to set it equal to 1/2 mv squared. In this case, we're using mass 1, so we're going to plug in the mass, and we're going to get K1 is equal to 6.75 kilograms times velocity squared. For K2, we're going to use the same equation, this time using mass 2, and then we're going to get kinetic energy number 2 is equal to 5.75 kilograms times velocity squared. Now, we have all of these little parts, but what are we going to do? Well, we're going to plug them in to this big equation that we made up here initially. So, we know energy final is equal to the potential energy 1 plus kinetic energy 1 plus potential energy 2 plus kinetic energy 2 plus rotational kinetic energy. So we solved for all of these. So now from here we can just plug in all of our numbers. We can do the algebra, and then we can get that the velocity is equal to 1.48 meters per second. So, now that we've made it this far, I would like to say what I struggle with in this problem. As I mentioned earlier, I did struggle remembering rotational energy. But before that even, I struggled because I was trying to do it all at once. And simply for problems like these, with a lot of moving parts, literally, it's best to break it up into individual parts so that we can make it easier for ourselves and make it easier to comprehend. Overall, that's what I learned, is to break it up into individual parts to help simplify the equation. Thank you. I hope you enjoyed.